Blocking and non-blocking assignments are very unique concepts for HDL like Verilog. At macro level, these are used for combinational and sequential circuit design. If asked in interview, do you know what happens at the micro level when each of these equations are evaluated separately? In today's episode, we will cover both the micro level analysis as well as macro level analysis through theory and hands-on example respectively. So stay tuned till the end of this episode for minute details necessary for the interview.
Hey guys, welcome back. In today's episode, we are going to discuss the below points. Introduction to blocking and non-blocking assignments. We'll use infographics to differentiate between the blocking and non-blocking assignments. Next, we will talk about blocking assignments and the mechanism by which it blocks. Next, we will talk about non-blocking assignments and its mechanism. We will go through thorough examples of blocking versus non-blocking examples apart from the small examples which we have given in the above points. Next, we will give a quick and to the point rules that you can follow while you are designing in the Verilog so that you properly choose blocking and non-blocking assignments in a proper fashion. Next, we will summarize our discussion and finally, we will go through some hands-on code which are not shown in the theoretical slides and do their simulation using Verilog and Vivado. That's the menu for today. So without any further delay, let's begin. Introduction. HDL such as Verilog have a striking difference in defining a value of a variable as compared to its programming language counterpart such as C language or Perl. In C language or Perl, two consecutive value assignments are as per the line-by-line execution of code. So focus on this thing, line-by-line execution of code. So this is the fashion in which the C language or the Perl works. Hence, in the C language or Perl, the playhead is the line counter. So what is called a playhead? So when you are playing this video, right, over time, a marker goes on from left hand side to the right hand side. So that is called the playhead. In C language, this playhead is vertically down, or in Perl, it is the same. So that playhead plays the code line by line from top to the bottom. Also, the playhead can hover around the code by calling a function, subroutine or named code blocks. These are some exceptions where the playhead can start here and go up to this point and then it jumps over to another point where there is a subroutine and then it goes back again to the main code execution. So this is the concept of the playhead in the execution of the code for C or Perl. Now we will go for the striking difference which we have mentioned in the first line for the Verilog. In Verilog, the playhead is the time step during the transient simulation and not the line number. So this is the very much fundamental difference. So in Verilog, the simulation can happen over time and your wave is going through like that, any wave. So I have not drawn a digital wave. If I am writing a digital wave, then it will go like this. And in this case, your playhead goes from left to right, from this direction to this direction. So this playhead is the time wise. That is, this is a transient simulation which we are talking about. This is a transient simulation and not the line number. So in C, the playhead is as per your code line by line. However, in Verilog, it is as per the timeline marker of the simulation. In Verilog, we do have the named code blocks. We'll cover it in some other episode. However, in that case, the jumping will happen inside the code and jumping back to the original point of execution will also happen. Hence, two separate code blocks, like two initial blocks, which you can easily write, staying far apart in the entire Verilog code can get executed parallelly. So this is the line of code. Here there is an initial block and here there is an initial block, right? So this and this can happen parallelly because your code execution is timeline wise, and in timeline wise at this timeline, this and this initial block will happen because the initial block is executed at the beginning. So rather at this point. So here this will start executing. So this is the fundamental difference between the C language or Perl and Verilog. So the playhead in the two, one is line by line code execution, and here in Verilog the playhead is the transient simulation. For this temporal nature of Verilog simulation, there are two types of assignment operators. One is a blocking assignment, another one is a non-blocking assignment. You can remember in C or Perl, we only have this kind of operator and we do not have this kind of operator. This is called in C or Perl, it is called less than equal to. Here it is a non-blocking assignment. Now the temporal behavior is nothing but the timeline wise response of Verilog. So this is called the temporal nature. To accommodate all that temporal feature or that transient nature of Verilog, we have the blocking and non-blocking assignment. Generally, the blocking assignment is suitable for combinational circuit logic of digital design. Combinational circuits, you know from the Carnot mapping and POS and SOP, you can design a combinational circuit. In earlier episodes, I have shown you how you can code a combinational circuit to various types of Verilog modeling. Whereas the non-blocking statement is used for sequential circuit logic of digital design. So you can see that the non-blocking is meant for sequential logic and blocking for combinational circuit. So this is a very straightforward thing to remember. Also, the non-blocking assignment allows designer to describe the state machine which update without needing to declare and use the temporary storage variables. So at some later episode, we will cover the state machine, and you can find familiarity with your already known circuits where the state machine is applicable. This is used for designing complex digital circuits and their states. There the non-blocking assignment is very useful. So for advanced VLSI design, the non-blocking assignment is a must. So here we are done with this particular slide. So let's move on to the next slide. Blocking versus non-blocking assignments. Here in this slide, we will use an infographics. We will use infographics to draw a straight difference inside your mind about the blocking and the non-blocking assignment. So here is our separator. At left hand side, we will have the blocking example, and in the right hand side, we will have the non-blocking example. So here you have a picture of a switch you are turning on, and you have connected a wire to a light. In this picture, how this signifies the blocking assignment. Here you can see this small cartoon character is plugging in or directly connecting the two wires of a light, which is a output, and here the switch as the input. So when both are connected in a direct fashion, that means if you turn this switch on, that will go, the instruction will go through this wire and turn the light on. So this is a very simple way to understand the blocking statement. That means the blocking statement directly assigns a value to a variable and make it fixed, make it like a constant. Now let us move on to the next infographics for the non-blocking assignment. Here you can see there is a conveyor belt, and in the conveyor belt is changing with time, because here you have different boxes with different articles that are coming in and they are going in a direction. So once this is inside a company, you have a counter where some processes are going on, and here the boxes are staying for a while, maybe for a labeling, maybe going for a destination. So it has to wait here for some kind of functionality, and it has to register here that this parcel will go out. And next, this whole thing comes to the final delivery point where our mailman is picking up the package for the delivery truck. So this is an explanation of how this picture is working in a real life. Now let me draw the similarity with the non-blocking assignment. Now here you can see the connection is very much direct. However, here whatever you are getting here as the delivery box, which is here, that is not directly what you are getting from here to here. So there are a lot of time steps, 1, 2, 3, everything will go through this checking. Here this acts as a playhead. Through this playhead goes, it passes on, it puts on the labels and everything, destination and etc., and then it comes to you. So here this thing cannot cross, this particular box cannot cross all these boxes and directly come to here before this thing. So this is a kind of concept of the state machine where different state will be executed in a particular sequence. And in non-sequential logic, right, where we are using a shift register or a register, there you can see the data traverses inside the sequential circuit in a particular manner. So this is the time-wise simulation, the time axis or the non-blocking, whereas this one acts as a playhead, right? This box, the counter where everything is labeled and sealed and checked and verified, so that acts as a playhead. And no matter you try, you cannot get this box here directly at the output counter. So this way the non-blocking assignment works. That means it has to follow a sequence. That means whatever is here, it has to be labeled, whatever here, it has to be labeled, whatever here, it has to be labeled, and this one is labeled, right? This operation, this labeling operation or checking operation, whatever you are seeing here, you will see in next coming slides. So that is done in the non-blocking mechanism when I explain with equations. That time this picture and the left side picture will be very clear to you. You have this picture in the video, so you can go back and use chapter to come back to this particular slide once you already traverse in the explanation in the later slide. We are done here and you have a glimpse right now. As we progress through the entire discussion today, you will understand why there is a difference between the blocking versus non-blocking assignments. Blocking assignment. Here we will talk about the blocking assignments. Blocking assignment or statements are continuous in nature, that is the same fixed hardware circuit connection. Here I have used a word hardwired circuit connection. Now you can correlate with the picture that I have just shown in the previous slide. This blocking assignment is a continuous in nature. Whatever we called continuous is analogous to the hardwired connection in the circuit. So continuous in the Verilog code means it is hardwired in the actual circuit. If you made the circuit on breadboard, blocking assignments literally block the execution of the next statement until the current statement is executed. So the blocking assignment will not allow for any parallel execution which happens in the non-blocking. You will see later. So you have to wait for some time for the entire explanation to come in front of you. Consequently, blocking assignments result in ordered statement execution. So whatever the blocking statements, they will execute one by one, obviously with the time as the playhead. Remember that. Here this ordered execution is not same as the ordered execution of C or Perl. This is in ordered execution of the timeline playhead. Example, we go for a short and sweet example here. We assign A equal to B equal to 0 separately initially. Then we assign A equal to 1. This is a blocking assignment. Here the B still holds 0. Next we assign B equal to A. Now A got assigned to B, and finally we have A1 and B1. Finally after the ordered execution. So the executions happen here first, then this, and then this. So it has a sequence of happening from this to this as per the playhead in time. Why I say the playhead in time? If we include here a hashtag delay, right? So the time playhead will wait for the delay to pass on and then it will assign. Here by the delay you can see that is by the playhead in time. Otherwise all the statements will be in a same timeline point and the playhead will play all together them in once. Digital circuits which have a race around condition in its truth or state table. State table is a term which you will find in the .lib VLSI world, the .lib or the timing.lib or the timing lib or the liberty file, and whereas you will find the truth table name from your class book. That means your textbook which you have read in your college days. I have given the both terms so that you can correlate. In case your digital circuit has a race around condition in its truth or state table, it cannot be modeled by the blocking statement. These are some rules where you cannot use. So later you will find what if we do a blocking in the race around, what will happen. The race around will happen and that will make the circuit unstable. Next, any kind of feedback path from output to the input cannot be modeled by the blocking statement. So you have a block where you have some inputs and you have some outputs, and you do have a feedback path that is working in some fashion, whether it is a positive feedback or it is a negative feedback. I'm not talking about that, but it has a connection from the output to the input as a feedback path. So that cannot be modeled by the blocking statement. Not the feedback path only, but the entire circuit cannot be done by the blocking statement. The results will be erroneous. Any single output pin getting values from mutually exclusive set of input combinations over changing conditions cannot be modeled by blocking statements. So you have a circuit, it's a block. Here your output is same. Here you have two inputs and here you have two inputs. So there are some combinational circuitry and you have some selection switch. The first one, if you change its value 0 or 1, the first two input combination will be connected through this, and these two, if you connect, right, if you change it to 1, these two will be connected. So you can realize this is a kind of muxing operation, right? However, in words we have generalized it, and it is not limited to the mux, but however, if there is some mutually exclusive set of input combinations, right, in any digital circuit, in any design, any complex design you come up which is much more complex than a mux, cannot be modeled by the blocking statement, because in such conditions where you have a combination which is connected with the output conditionally, so it acts as a switch here. So either it connects to this or this, so it is not fixed. That means it is not hardwired to any of the input. The output is not hardwired to this combination or hardwired to this combination. So this way it is very much different, and you can easily understand the blocking statement means that you have a hardwired connection. The hardwiring that you cannot change with the time. This is a blocking statement in a nutshell. We are done with this slide. Let's move on to the next slide. Blocking mechanism. Now let me go through the example to make you understand how the blocking mechanism works. Here we have a always block, and in the sensitivity list we have A, B or C. Any of them changes, the always block will become active and it will execute the code inside this. Here we begin our codes with the begin keyword. Here the first statement is X equal to A and B. Evaluate A and B and assign it to X. So this is the immediate execution. So this happens very immediately from this side to this side. Next, Y is equal to A or B or C. Evaluate this logic equation and assign it to the Y immediately. Z equal to B or C. Evaluate B or C and assign the result to Z. So these are happening instantaneously. That means once the playhead reaches this point, this assignment takes place from RHS to the LHS. Next the playhead reaches here, it happens from here to here. Next the playhead reaches here, the assignment happens from here to here. So this way the blocking assignments, that means these equations are hardwiring the inputs to the respective output. So here you can see there are common inputs and they are getting hardwired with the output, and we end the always block with the end keyword. So here is how the blocking mechanism works. We are done with this particular slide and let's move on to the next slide. Non-blocking assignments. Non-blocking assignments allows the instant state transfer and state change operation. Non-blocking assignments literally do not block the execution of the next statements. So the non-blocking assignments allows the instant state transfer. So later we will explain how this instant state transfer happens and state change operation happens. There are two steps, state transfer and state change. I will later in the mechanism slide, in next slide I will explain this. And here it do not block the execution of the next statement. So here until one statement is executed, it's not like that the next one will hold on for the execution. So it's a different, you will understand in the mechanism slide coming up next. The right side of all statements are determined first and then the left side are assigned together. So this is the theme. That's why it do not block the execution. That means the RHS and the LHS. RHS happens parallelly, all the calculations and blah blah blah, and they are assigned in a one go to the left hand side equations. Consequently, non-blocking assignment result in simultaneous or parallel statement execution. So here it is much more realistic because in real time, when you are having a real time data going on, the many things, many assignments or state changes will happen concurrently. So the concurrent thing has to be addressed inside the Verilog, and that is addressed by the non-blocking statement. For example, A equal to B equal to 0 initially, below two are executed simultaneously together, that means in parallel. So first this one, this is 0 first, right? And 0 to 1, this state change is happening here. the state change, and B, here it's a non-blocking operator. You can see we are using non-blocking. Let me clear it, and you can see here we are using non-blocking operator here, and here you can see the state transfer. So here I have just kept the state change from 0 to 1 by this non-blocking, and this 0 goes to B as a 0 as a state by this one. These two happens parallelly, the RHS, and then in one go they are assigned to the left hand side. And after execution, what happens? This goes to A, one goes to A, so A is 1, and this goes to B, so B is 0 after the parallel execution. So it is very much striking difference from the blocking assignment, or you can have a literal difference from any programming language that you have in pen or paper you are solving, right? From there it is very different. The digital circuit that are modeled by non-blocking assignment. Now we will have a list. Any sequential logic circuits. Next, a race around condition which exist in the truth table or the state table of any digital design. Those are expressed by non-blocking assignment. Sequential logic and race around conditions which are in the state table. Any kind of feedback path from the output to input if exists, right? In that condition, what will happen? The state transfer from the output to the input. So here to here will happen, and here to here will happen, but this will be calculated first and then assigned, and this will be calculated first and then assigned. So this way this is handled, the feedback path is handled. Any single output pin getting values from mutually exclusive set of input combinations, where we have a mixed situation, right, where we have separate inputs and single outputs, and over time the selection can happen from this to this or this to this. This is perfectly taken care by the non-blocking assignments. So the limitations of the blocking assignments are overcome in the non-blocking assignment. So here we are done with this particular slide. Now let's move on to the next slide. Non-blocking mechanism. Here we'll go through the mechanism. Here we have the same always block which we have used earlier. A, B or C in the sensitivity list. So any of them gets changed, the always block code will executed. We begin the code with the begin, and then we have the first assignment here. So X has a non-blocking assignment from A and B. Now how this works? Evaluate A and B first. So this evaluation happens at first, but defer the assignment of X. So that means it halts here after the evaluation of A and B. It halts and defers the assignment and wait until some point. We'll come at later. Next, evaluate A or B or C, but defer the assignment of Y. That means halt here at this boundary. That means up to these two, this has executed and evaluated, this has executed, evaluated, but halting here. Next, we have B or C, which is assigned to Z by the non-blocking. So the B or C is evaluated, but it is deferred for the assignment to Z. That means these three are evaluated but halting at this boundary. Now we have exhausted of all the equation and the non-blocking assignment. At this point, what will happen? All of these will be assigned in one go with the left hand side. So the LHS will be assigned in one go with the new values from the RHS. So here you can see that the LHS assignments will happen in one shot from the right hand side, where all the evaluation was happening and they were halting at the boundary, this boundary. So they will get assigned in one go once all these non-blocking assignments are evaluated. And one more thing here, all these evaluation will happen parallelly. That means this will happen parallel to this and parallel to this. So they are not sequentially happening, but for sake of explanation in the slide, I have to show you in sequence. However, in actual circuit, they are happening parallelly. And here we end our code. That's all. We have explained the non-blocking mechanism. Let's move on to the next slide. More blocking versus non-blocking examples. Blocking examples, x equal to 0. Here it means that x changes at t equal to 0, and the next one a equal to 1, a changes at t equal to 0. And here we have the delay added, hashtag delay with 10. So 10 time units delay will be there. So delay until t equal to 10 and then c changes. So t means the marker, the playhead will wait for 10 time units and then c will change. Here the 15 delay units are spaced in front of D and it is assigned to 4. So delay until 25 time units and then D changes. So just to make you understand, so after this doesn't mean this is at t equal to 15, 10 and this is 15. So if you see, right, 10 and 10 plus 15 is 25. So it is added. So once you move from here, it is added. So these are adding timing spaces. Equal to 5, E changes at time t equal to 25. So we'll go to the next non-blocking example. So you have seen how it is happening with time. The playhead is time. So since we do not have a delay, they are happening at 0. Here we have the timing separator of 10 units. So at t equal to 10. 15, so 10 plus 15, 25, at this is happening at 25, and here is no time delay here. So this is happening at t equal to 25. This way, the timing playhead moves on and the instantaneous assignments are happening through the blocking examples. So now see similar examples in non-blocking assignment. This schedule to change at t equal to 0. That means here we have nothing to evaluate. So it is scheduling to change at t equal to 0 once all the non-blocking assignments be exhausted. So here evaluate at t equal to 0, schedule to change at t equal to 15. So that means once t goes up to 15, this value transfer will happen. Now here it is the same, evaluate at t equal to 0, schedule to change at t equal to 10. It is not sequential, so you can see the difference here, right? This is sequential, so these two are getting added. So 10 plus 15 is 25 here. However, this is very much individual. So this one is 15 and this is 10. So they are very much individual and they are happening parallelly and all are scheduled to change. Next here, this C or 1 evaluate at t equal to 0 and schedule to change at t equal to 0. So you can see all these right hand side things are scheduled for change at some particular time. So somewhere it is t equal to 0, somewhere t equal to 15. Okay. And when this will happen, this evaluation will happen parallelly and they will be assigned in one shot from left hand side to the right hand side. However, if delay is added, then that assignment will be done after some delay. So these are the examples of the blocking and the non-blocking examples. Let us see some more blocking and non-blocking examples. Blocking, A and B end up with the same value, the race around condition. Here we will show a race around condition by the blocking statement. This is we are talked in the initial slides in this episode, and here we are giving the example. Here always at the posage of clock, that means we have a clock and in this positive edge we are sensitizing the clock. So once this positive clock edge comes, do these operations. A equal to B, change now, and we have another always block. You remember these and these will happen parallel. These are fashioned to work in this way. I have explained in previous episode. And B equal to A, changes B to a new value. So they will happen parallelly, these two always block, and they will be assigned. So you can see here B is assigned to A and here A is assigned to B. So this creates a race around condition because we do not have a control what is happening first and what is happening second. So we cannot decide what value will go where. Next, we have the non-blocking example of the same kind of operations. Here we use the same kind of always block and sensitized with the positive edge of the clock. And here we write non-blocking assignment of B to A. So read B at t equal to 0 and schedule to change for A. In the same fashion, we have the another always block where A is read at the t equal to 0 and schedule B to change when there is a sensitivity of the clock. Here these two happens parallelly, that means they are scheduled to change. So that means these are evaluated and whatever value was in B will wait to go to A and whatever value is at A will wait to go to B. Since they are not hardwired and these assignments will happen at the coming of any positive clock edge, the value which are staying in a kind of temporary register, they will be transferred to the respective variables in a ordered manner and the race around condition is avoided. So here we are done with the examples of the blocking versus non-blocking. For a race around condition, you can simulate it by your own code and you can see the results. some rules to follow. So here in this slide, we will make some rules for you to follow so that you do not get confused in actual Verilog design. And remember all the points that we have discussed so far. And with this set of thumb rules, you are well equipped to use the blocking and the non-blocking assignments. Blocking is used in always and without the clock. So we have a always block, and hence here the sensitivity list is tell that is selection A or B. So any of them become active or become their values changes, right? That will trigger the always block to execute the code inside. Case cell, so this is the first case, B goes to A. This is the second case, B goes to C. Sorry, this will happen. So A goes to C and B goes to C. So this will happen. And here we end the case. We will come up to these all procedural blocks like case, if, else, all these things later on. Before that, we have clear our minds about the Verilog coding, because these are very, very similar to the Perl or C language wherever we have used the case or if or else. So you will be very much in ease to accept them. However, the hard nut which is we are cracking here before we are going to our usual easygoing things, so that you are very much equipped in your mind. And here we end the always. So here you can see here do not have a clock. However, we have a muxed input, right? Here you can see different cases are there. It is not a mux in digital circuit nature. However, it's a muxed input. So different variable conditions here and it will go there. So here there is some typo here. O has come instead. It will be 0, B00. It's a typo, sorry guys. And in such muxed condition, we use the blocking inside the always block. And remember, we do not have a clock here, but we have a muxed input from where the selection go to the output for multiple input conditions. One comment here you can use it. The blocking can be used. However, it is better to choose the non-blocking assignments. Blocking is used in continuous assignments. Like here, you can see we have used the continuous assignment here. This is the case where you can use a block where you do not have a clock. However, you have a muxed input. Better you can use the non-blocking. However, this you can use. So you have some relaxation here. Non-blocking is used in only inside the always with clock or muxed input. Here we have the always block and we have the clock, passage of clock or negage of reset, and we begin our code. And here is the if condition inside which we have the counter, right? And here we have the else, and here we have the another value of the counter plus 1, and this is 0. And here we end our code. Here is also there are two conditions. That means here is a muxed input. So if there is one condition here, right, we go for this, and here another condition is here. In such condition, we are using the non-blocking operator. This, however, you can use, but it is preferable to use this one. And this is the case where it is hardwired is the continuous assignments. So there you must use the blocking operator. This slide is good for your Q&A for the interview. Remember these things. So this could puzzle you. So if you given side by side this example and this example, right, it confuses you. This is okay, you can do that, but preference is on this one. This should be done. Now the question is why? The question, because here two cases do not overlap here, right? So either this will happen or this will happen. So here this will happen or this will happen. So any one will happen. However, the hardwired thing is not good for such selection. Better that you use the non-blocking assignment. And for continuous one, which are continuous in nature, that means hardwired, input and outputs are connected together, you use this thing, the continuous assignment. Now you are well able to correlate the infographic slide up to this. When we have given all the examples, you can understand why the continuous one is a hardwired in nature, whereas the non-blocking assignment very, very different, which was explained by the right hand side infographics. These are now, I think you are clear to you. You can go back and forth in the particular image of the infographics. There you can go and come back to this slide and correlate these things. If you are a beginner, right, this thing will puzzle you for some time, but after you do the coding in hand, you will get everything clear. So here you are done with this particular slide. So let's move on to the next slide. Summary. Blocking statements x equal to y, executed in ordered manner as listed, including any delay specified. Here the evaluation and assignments are immediate from RHS to LHS. So this happens in a very immediate manner. one statement realized before the next statement is executed. So it is very sequential in nature. One is realized, then another at time t equal to some value. All the statements will execute sequentially. That means this to this, and this sequence at some particular time. So time will not change. However, inside the time, all this equation will execute sequentially. Will not block execution of the statements in parallel blocks. So parallel blocks will happen in a parallel fashion, like multiple always block or multiple initial block. Useful for modeling digital combinational circuit. For combinational circuit, we use the blocking assignments, also called the blocking statements. Non-blocking statements, that is, here we can read out this as a non-blocking. So less than equal to sign, although it means we are non-blocking assignment, it is here. Schedule assignments without blocking other statements. Execute next statement without waiting for the first statement to execute. So that means if we have all the statements, and here is the separator, here is the LHS, and here is the RHS, all of them will happen, evaluation will happen, and the transfer from RHS to LHS will be done in one go. Assignment is postponed until all separate RHS evaluations are done, then assigned in one go from the respective RHS. So this is we have explained, which is a very much striking difference between the blocking and the non-blocking assignment. Useful for modeling sequential logic circuits. So this is very useful for modeling sequential logic circuit. So we are done with the summary here, and we have the striking differences. The blocking is one for combinational circuit, the non-blocking is for sequential circuit, and how this thing happens we have also explained throughout the episode, and we have summarized in the summary slide. So let's move on to our next section where we will do the code simulation. Hey guys, now we'll do the hands-on testing of the code of a 4-bit shift register. So here you can see the circuit diagram here. Here this is our input bit, and here we will measure the outputs, and we have a clock input and a reset input, and that goes to all the clock inputs of the D flip-flop, 4 D flip-flops here. So this is a structure of a 4-bit shift register, and this is we are going to implement through the behavioral modeling in our Verilog code. So let me open the codes. I am using Geany here. So here is our terminal. So here you can see, as I have shown in the picture, here are the input and outputs listed. So here is clock, reset, and A, B, C, D, E. We mentioned output here and input here. Don't worry, you will get the download link of this code in the video description. From there you can download the code and do your experiments. Here we have a always block, and here we are specifying the reset condition. If it is reset, then all this will be 0. And this is happening the positive edge of a reset, and else if it is not, we will go for the assignments. So this is the blocking assignment. You can see here all blocking. So we will use the same circuit, and we'll change the assignment here only as the blocking to non-blocking. Rest of the code will remain same. And here you can see the test bench, right? And here is our clock. It is our clock definition. Here the clock is start with 1, and after every 5 time unit it's toggling. And here you can see we have created a dump file, although this will not much be needed in today's example. However, as per convention, I have kept it. Here you can see this will print the data table, and this monitor will monitor all the changes in the mentioned input outputs. And here we give our test vectors. So you can see in time 0 we have given E, which is our input, as 0, and reset as 1, and then at 7 time units we have used the 1 and 0 for the E and reset. In first case the reset was done, and in the second case reset is removed and value is assigned together. And here we have instantiated the module which we have defined in the beginning of the code. That was blocking assignment. Here everything remains same, except we have non-blocking assignments here, and rest of the things remain same here. Let me give a diff in between the two. I am using TK diff here. to diff between the two Verilog code. And here you can see the difference points have been highlighted. First, here all are blocking and same are non-blocking assignment here. This is also blocking and this is non-blocking. If we come down right here, we see the difference in the dump file name, the VCD file name. Obviously it will be different for the two, and we can see the instance of the module here. You can see the shift reg BK, which is the blocking, and shift reg NBK, which is shift reg and the non-blocking, so instance NBK. So here you can see this and this are different. So it's very clear that in this, among these two files, we have only few difference points as the blocking assignments and the non-blocking assignments, and the instance name or the module name and the VCD file name. So rest of the things are, you can see here, all these and these are same. Also that is true for part here, these are same. So with that note, let me simulate these codes. I am using Icarus Verilog. The command is iVerilog, and then we give this and we give the output dump file name BK. It is a blocking one, right? Let me generate the two object files first. Now I do a ls. You can see here that two object files with BK and NBK has generated. Now let me execute this object file one by one. First, second. Since it's a shift register, what will happen? The value is assigned at E and that will propagate in this direction. The value will shift with the clock pulse. So you can see here at 7 we have set the value right, and since this is, we have used blocking assignments, and here you can see the value has changed. E is 1 while we have done reset for all, and since we have used blocking assignment, all have become 1 here. We exclude the clock. We are not talking about the clock. We are talking about the data inputs and data outputs. We are not talking about the clock. You can see that all have become 1, which is not expected, right? Because we are expecting the bit to shift left. Now we see the result of the non-blocking. So here you can see the non-blocking, the NBK we have, and here we are not talking about the clock is properly toggling here, and here you can see at 7 we have set the value E to 1, and because of the reset instruction given previously, all are 0. So you can see if we follow this line, the bit 1 has been shifted down with the clock pulse from E to D, then D to C, then C to B, then B to A. So this way the bit has shifted from here to here. So with the non-blocking assignment, we have achieved the shift register design. If we use the blocking assignments, we are not able to get the desired outputs. We have done the simulations with Icarus Verilog and we have used the Geany IDE here. Let us move on to the Vivado. Let me close the Geany. So Vivado is starting here. You can see here it is starting the GUI. The splash screen has appeared and our Vivado interface is ready. So we will click on the create project here. We click on next. Name it 5 and you can see here it is opening in the right correct. And here we choose the RTL project and do not specify the sources at this time. These two options. Here everything is okay. Let it be. In the boards, we will pick this one. Although we are not using a board, we click on finish. So it has opened. Now we will click add sources. Add or create design sources. So we go for this option. Go to add files and we add the shift register with the blocking assignment, and here you can see the preview in the right hand side. So you can see what code you are opening, and here we click on finish. So here on right hand side our code has opened, and now we will go for the run simulation option. So here you can see the output has came for the printing statements, and the first one is clock. If we set aside, we can see the clock is toggling properly, and there is a bit shift in the A, B, C, D, E. You can see at 7 E is set to 1, and because of the reset instructions everything else is 0. We are not talking about the clock here, we are excluding the clock, right? You can see that because of the blocking here all are 1. So we don't see a bit shift here. It is not shown here, which we have seen with the Icarus Verilog simulation also. Let me now go and add sources. Here we will pick again this option, and here we will use the non-blocking Verilog code, and here we go for add files, and here we add shift reg NBK, and in the right hand side you can see the code preview. Click on OK and we say finish. So we are removing the blocking one here. So here you can see the non-blocking code has came here. We will do the run simulation. So here you can see the output has came for time and clock. We can see the clock is properly toggling, right? We can see at 7 E is set to 1, and if we carefully look, right, this bit is getting shifted towards the left following this line. So it is going from E to D, D to C, C to B, and B to A in this fashion. So with the clock edge the bit is moving left. So with the non-blocking assignments, here we have the non-blocking Verilog file and the corresponding simulation. We can see that with the non-blocking assignment we have achieved the shift register, the operation of the shift register here with the Verilog code. So we are done here with the example. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.